Okay. Hi everyone, welcome. I'm Andrea Angela, and today in this video I'm going to share with you the solution for the further problem solving and programming skills A2 level computing of May-June 2017. And let's start. Okay, so the first question is about assembler. Okay, this is a big table with all the classic instructions that you should be all familiar with. These the assembler language, the immediate addressing, direct addressing, indirect addressing, indexed addressing, storing the content of the accumulator of the email address, increasing, decreasing, comparing, and jumping. So we'll get into that when we need to do the problem. So we need to write a program using the this instruction set to read a character from the keyboard and output the alphabetical sequence of characters from A to this particular character. So for example, if you insert G, you need to print A, B, C, D, E, F, G. Okay, so you are quite guided in order to write this program. So you don't need to write it completely. So you have the comment and you need to write the operation, the opcode and the operand. So let's try to do this and understand the program along the way. So the first things you need to do is to input the character. So you can actually look at the table and see that the input instruction is actually in. So let's write in. So this is actually taking a character from the keyboard. You can actually see in the table here, in, key in a character, and store its ASCII value in the accumulator, okay? Now we have the value in the accumulator, and we need to store this value in char, in the variable char. Char is actually this location of the memory. So let's store this in char. And the store operation is what we need. Store in char. If you go back to the table, store, where is it? Storage at a particular address. It stores the content of the accumulator at a particular address. So the first two lines, basically reading a character from the keyboard and then storing this in the location of the memory at the address char. Then we need to initialize the accumulator with the value 65. That is actually the letter A. It's the ASCII code for the letter A. And to do that, you need to do an LDM operation using 65. That is the address. So LDM, if you look at the table, is the immediate addressing. So load the specific number that you provide in the instruction to the accumulator. Okay, and then we need to actually print it. So out is what actually we need in order to print this to the console. So what actually happens is that we start from A and then we print A. The idea is that we should kind of print the next letter every time, right? So this is the third line is kind of an initialization. So start from A, then we will increase the value later. Okay, so we need to compare the accumulator with the character. Okay, so this means that we need to do a comparison of car to car, and based on this comparison, we want to, if equals, we want to jump to the end of the for loop. So that means that if we actually arrived, the character that we just print, that is at the moment in the accumulator, is exactly the same as the one that the user inserted at the beginning of the program, means that we finished. All right, so we want just to jump, so is stay for equal to the end 4. Oops, sorry, let me start a bit earlier, and 4. So this means that we'll skip these two instructions and we'll jump to here, and then we'll end the program. If not, it means that we need to actually print other letters. So we haven't actually finished. We need to increment the accumulator. So this will actually move to change the value of the accumulator to the next ASCII value. So that will print B, that will print C, and so on. And then we need to actually jump to loop. And where should we put loop is the question. Loop is actually must be a label, right? So at the moment it's not present. What we need to do is actually, as soon as we increased the accumulator, we need to actually print it again. So we need to do it here. We want to print. If we don't want to do it one line before, otherwise we will set the accumulator again to A. So we will just always print A, and the program will never terminate if you insert a character that is not A. So, and this is actually pretty much it. So this is basically the code that solved this problem. The next question, we run a program that tests if a 8-bit 2's complement integer stored in the address number is positive or negative, and if should output p if it's positive and n if it's negative. So if you know a number is positive, is the first bit is 0, or negative is the first bit is 1, using 2's complement. So we actually want to write some code that check that the first bit is 0, 1. And based on that, print p or n. So let's do that. Let's try to fill this table. So there's some gaps here. So it's not immediately obvious what we want. So the mask is basically something we need to use in order to do the comparison. We already know that we are going to need to do an AND operation. So here with the mask, because we know that if we do an AND of the accumulator with the mask, it means that if the mask is set in a way that only the first bit is set, all the bits will be set to 0 except the first bit. So mask is going to be set to a value that is the binary value 10000000. Okay, so if you do any number and 10000000, the result will be basically a number. Will be basically a number that is 0 if the first bit is 0, or a number that will be exactly the mask if not. And but we haven't actually, the AND operation actually used the accumulator in order to do the AND operation. So we haven't actually loaded the number into the accumulator. So that's why we have the initial instruction here that must be to load the value pointed at number into the accumulator. So LDD, if you go back to the table, is actually the direct addressing. So you provide an address of the memory, and this will be loaded into the accumulator. So we need that in order to load the number. Then we do the AND. Then we compare with 0. So if it's 0, it means that it's going to be positive, the number, right? So if the is not 0, we need to jump to else. Otherwise, we know. So if it's 0, we jump to else. So we actually skip these two instructions, and then we go here. If it's not 0, so the comparison is not 0, we'll go to the else. Otherwise, we carry on. And what we want to do here, if we know that it's 0, we actually want to print p. And we know that the ASCII value is 80. It's been provided in the comments. So we want to load 80 to the accumulator in the accumulator, and then just print it. So let's do LDM 80. Oops. LDM of 80. So this will load p in the accumulator. And then we do a jump and if. And in the end, if we must print whatever we have in the accumulator to the console. While if we when we jump to else, this means that was not equals to 0. So this means that it's actually a negative. So we need actually to load the ASCII value of the character n into memory. To do that, we need to do LDM 78. And that's pretty much it. So that's the idea. You load the number in memory, you do an AND with a mask. If it's 0 or 1, you print p or n. Okay. Next. So now we need to kind of implement some operation about an hash table. We want, there are three operations: creating the hash table, inserting a record, or searching the hash table. So if you're not familiar with it, so an hash table is basically is a key value container. So the idea is that given a particular key, you will be provided with a particular value, right? If the key is not present in the hash table, the value will be null, or there will be an exception thrown. It depends how you implemented it. So the idea is that it's a data structure that allows you to store key value pairs in a very efficient way. The search, the access to a particular value is incredibly quick. It's like accessing a variable. It's all close to that. So we want to actually implement this. So before doing that, we have a user-defined type that contains a customer ID and the data. So the hash table will be implemented as an array of customer with the elements indexed from 0 to 199. That means there will be at maximum 200 elements in the hash table. And we want to create the procedure to create an hash table will declare and initialize this array by storing 200 records of the customer ID field in each records set. So here, what we really want was what we've been asked you to do is actually to initialize an array of 200 elements of type customer record and set the customer ID to 0 for all of these customers. Okay, initialize the hash table, and because we set the customer ID to 0, it means that we use that as a way to say that there is no information in it, right? That is empty. This is not used. So what you need to do first is declare this customer array. So here we need to use pseudocode. Declare customer array 1 to 199, and of the type must be customer record. Okay, and then what we need is a loop. We need to loop across all of these elements. So let's do a for x. Let me do left arrow this way. 0 to 199. In that case, you need to take the element in position x and then dot customer ID and set this to 0. Basically, for each element in the array, we set customer ID to 0, and then we need to end the for as well. Always close the for statement. This is actually the code that created the array and initialize it. So next, so there's an hashing function called hash that takes as a parameter the customer ID and returns a number between 0 and 199. And the procedure insert record takes as a parameter the customer record to be inserted into this hash table. So the idea is that the procedure uses the hash function in order to calculate the location inside the hash table where this record should be actually stored. But there might be collisions because there might be it's possible that the hash function will return the same location for different customers. So if there is a collision, the way this problem is resolved is that we basically loop. We move forward until we find the next available location in the array, and we store it. This means that if we want to access the information later, and it might not be immediately present exactly at the location of the hash function. We'll get into that later. We've actually been asked to write that code. So we want to actually write a procedure that the procedure will generate an error message if the hash table is full. So we want actually to write the code that insert a particular record into the table, in the hash table. So we pass the new customer to it, and then we have to fill some code. So if you look at that, you can see that. So the first things you need to do is to generate the hash value. So you already know that we have a function hash that take a customer ID. And so we know that the customer ID is actually a field of the customer data structure. So we can actually access that ID. So now index is actually the location where we want to try to insert the record. And then pointer is index. So it is basically creating a temporal variable because we want to be able to scan the list in case the location of the index is not empty. So we need to find a free table. We need to find a free table element. So until the location in the hash table is not free, so how can we check that? We already kind of decided that the assumption is if customer ID is 0, it means that the location is not used. So we need to check for that. So if customer at the location pointer, so let's use pointer here because we are going to change that later. If customer at the location pointer customer ID is different than 0, it means that is busy, so is already used. So we need to move on to the next location. So that means that we need to increase the pointer to 1. Okay. However, the hash table is not infinite, so it's made of 200 locations. So if the pointers goes above or equals 200, we need to wrap up to 0. So that's why we have this if. So if the pointer is greater than 199, we need to set it back to 0. Makes sense? And afterward, what we need to do, check if back to the original index. What does that mean? The problem is that obviously there are two. What happens if the hash table becomes full? You actually increase pointer, and maybe wrap ups, and then increase. At some point, pointer. How do we know that is full? If we can't find a spot, if we do not provide any sort of logic afterwards, the while loop will never end because the customer ID will always be different than 0 because it's full. There is no element with customer ID set to 0. So the only way for us to know that we actually try to check all the locations is when pointer is equals to index. That's why index we created a variable pointer. So index, remember the initial location where we actually looked. So when we've done all the scan of the hash table, if index is the same as pointer, that means that we actually looked at all the positions, so the table is full. And honestly, here, this should actually end the program, should actually return the function after the table full variable is being set. And afterward, there's some else. Okay, so it's here actually we need to do the printing. So if you look at the problem statement, it says that you should print an error message if the hash table is full. So actually, we want to do that. But also we want to actually add the new customer into the hash table. We haven't done that yet, as you can see. At the moment, we are the only things we did is actually to set a pointer to the location where we know that to a free location if exists, where we actually want to save the new customer. But if the table is full, we know that there is not a location. So if the table is full, we want to print the error message. So we output error. Right? Otherwise, we know the table is not full. Actually, we want to add the new customer into the hash set. So in this case, we set pointer to new customer. So we set the new customer at the free location that we found, and this is pretty much it. It's not very easy. So you need to really understand how an hash table works, and it's probably good things for you to do is to try to convert this code into Python and have a go and try to play a bit with it, because it's probably easier to understand if you want to actually try with some real code. Next, we have a function that search into the hash table. Okay, given the search ID, we want to. So let's have a look. The function takes as a parameter the customer ID to be searched. The function returns the position in the hash table where the record has been saved. If not found, we return -1. Okay, that's a fairly classic thing to return to represent not an index that doesn't exist. And we have a function called hash table. Search hash table. Okay, the first things to do is to generate the hash, and that's something we know. So we take the customer ID that is being called search ID for some particular reason here, and then we generate the index. Then we need to check each record from the index until found or not there. So what does it mean? There's a hint here. We need to check two things. Why? So let's try to understand what we are trying to do here. So index will be the location of the location where the customer ID should go if there is no collision. Okay, so if is the customer the customer ID at the location index is 0, it means that it's free. All right. If instead is is search ID, it means that actually we found the value. Okay, so is to increase index, so moving. So if there is a collision, we need to increase index. So what we want to do here is index equals index plus 1. Okay, and we want to do that as soon as there is a customer ID or as soon as we find an empty spot. So the way to do that is like that. If customer ID is different than search ID, we haven't found the location, we need to carry on. Or if customer ID is different than 0. So this is a bit tricky to understand. So the idea is this one. So if everything goes right, so index will be immediately search ID, right? So the location will be where the customer data will be found is exactly at the where the hash value of the search ID will be. So the while loop will stop immediately. However, if not, we need to carry on adding index as soon as we find the search ID or we find a free spot. If you find a free spot, it means that the search ID is not present. If instead we find the search ID, it means that it's present, but not at the location where the hash function provided, because there was a collision at the time when that particular search ID has been added. So, and again, when we increase index, we still need to wrap because we know that it must be below 200. So if it goes above 199, index need to be set to 0, same as before. So at the end of the loop, we either found the customer ID to be search ID at the location index or 0. So based on that, we know that we found the customer or not. So if the customer ID at location index is equals search ID, it means that actually we found the element in the hash table, and then in this case we want to return the index, because remember the function here won't return the index of the element if found. Otherwise, return -1. Index is actually the location in the hash table where the customer with the customer ID equals to search ID is present in the hash table. If not, we return -1. Again, I recommend you to actually try implementing this in Python to get a better understanding of how this works. So the next question is, a record that is no longer required is deleted. State the problem that might be caused by this deletion. Okay, this is very important. So if you understood the code here, you know that if you remove a record, it's possible that these algorithms kind of stop when the customer ID becomes 0, even if maybe a bit later the search ID is present in the hash table, but we will never reach it because it's basically not in a consecutive set of customers, a list of customers basically. So the risk here is that, how to put it, some records that were not at the exact hash index, that means there was a collision at the time when they were added, may not be found. Okay. Okay. Let's move on. Okay, the next exercise is we have an array called name list of 100 elements of type string. The programmer wants to search this list using the binary search algorithms. And the binary search algorithms takes the name of the string to be searched, the start index and the finish index of the list. And the function will return the position of the name in the list, or -1 if the name is not found. And basically, you are asked to write a pseudocode that implements the binary the binary algorithms. So the whole idea is that the assumption is that the arrays is made of strings that are ordered, so that are basically ordered, and it basically looks at the middle of the array. If it finds the element, fantastic, that's actually the location. If not, looks if the string is actually lower or greater than the one that is actually found in the middle, and then start basically do the search on the left side of the array or on the right side of the array. Implement this and see if we can get by. So the first thing you need to do is the base case. So these actually are recursive algorithms that will call itself on smaller and smaller arrays until you find a solution or not. Start and finish, at the beginning is start is 0 and finish is actually the length of the array. The base case is when because start and finish will get closer and closer and closer as more as we go down in the search. At some point the two index will cross over, and when they cross over, so when finish becomes lower than start, we want to return -1. Alternatively, if not, it means that we need to do the search. So we need to find the middle element of the array, and we do that doing the start plus finish divided by 2. And then if the string at the location middle is exactly the name we were looking for, this means actually we found the location that is middle. So middle is actually the index in the array where name exists. Okay. Otherwise, it depends. We need to search. We need to check if the search item is greater than this value we actually found. That is name list middle. So if the search item is greater than name list, it means that must be on the right-hand side, on the right subarray. All right, in the right half of the array. So this means that we need to actually call find again, passing name, and instead of using start as the initial element, you use middle +1, and you use finish. So basically, finish remain the same, and we move the start to the middle. So this means that at the next iteration, we are only looking on the second half of the array. If instead the search item wasn't greater than name list middle, we need to look at the first half of the array. That means that we need to keep the start index as it is and move the finish to be middle -1. This means that this will be start and this will be middle -1. It's very important to do the -1, the +1, because we always want to make start and finish closer and closer as we go. We want to be able to the algorithms to actually finish. If we don't do -1 and +1, the algorithms might actually iterate forever. So it will actually generate a Stack Overflow exception. So we definitely want to make sure that the algorithms converge. We always want to do that for recursive algorithms. And this is actually the implementation. Again, it's very hard to do this on paper. You need to try to write this in Python, for example, and play with it and try to understand how the algorithms works. Excellent. So then the next question is about the abstract data type. So we have an abstract data type that is a linked list. We want to be able to implement create list, add item to the list, and print the list to the console. And we want to do this using object-oriented programming as a list of nodes. So first we are asked, so we have two classes, a linked list and node. So a node is basically a single node of the list that contains the data. And the linked list is actually a collection of nodes, a series of nodes that are connected together via pointers. And what's the relation between these two classes? So what we really want actually is, so a set of boxes that are, so let's say a node is kind of a node of the list, and that they are connected between each other's with the arrows like that. So the linked list is going to be a class that contains a collection of nodes that are connected together using pointers, and the node will be actually the individual node of the list. All right. So what's the relationship that they have? This is called aggregation. So aggregation, it means that a class contains other classes. Like linked list will contain multiple instances of nodes. Okay, and to represent that, you can do that using. Let me try to take that. I'm going to change the color. I'm going to change the color easily here. Let me change that to that. So I have basically I can have something like that. Linked list. So I've been asked to use a diagram to express this relationship. So the relation is that each node can only belongs to a list, a linked list, and a linked list can have 0 to multiple nodes. So you can represent that using a diagram like that. So let's create the other element that is node. You could either do that, or you could actually add some lines here to represent the, usually, oops, this once again is not colored as I want. Fair enough. Let's do that. So usually when you use this sort of notation, you can actually specify the name of the methods and the name of the properties inside the various classes, but you've been asked not to actually list attributes and methods of the class. So you don't really need to do these lines, but you can actually do it if you want. And then you can connect these two. Oh, I really don't know how to. Let's try to do with a pencil. So usually you do something like that to do an aggregation, a kind of a diamond that is colored inside, and you connect this with the other element. So this means that linked list is an aggregation of nodes, and then you put numbers in either side. So the number here will be 1. That means a node, you need to read it in the opposite way. So a node can only be aggregated inside one list, right? While a linked list can have from 0 to star nodes, so any number of nodes. That's actually how you read it. A linked list can have from 0 to multiple nodes, and each node can only belongs to one list. And that's actually how you can represent this relationship. Okay, so now we are actually going to do the fun part. That is actually writing some code, use the real code using a programming language, and we are going to use Python. And I already kind of have written the code in an editor, because it's something I always recommend. Obviously, at the exam you can't do that, but it's always good to get familiar with the syntax using an editor, and then also do some practice as well on the paper later on. Depends on which stage you are in the process. So the closer you are to the exam, the more strict you need to be, and try to do in the paper first, and then try to type it into an editor and see if you made some syntax error or anything like that, or some logical errors. But if you are at the beginning of the learning, you need to kind of, I advise you to start immediately using an IDE so that you can actually learn the language along the way. Okay, so we have the node class that contains two attributes, data and pointers. Data is a string and pointer is an integer. And the methods create node, set data, set pointer, get data, get pointer. What you've been asked to do is to actually write the constructor of the node class. And the constructor is actually initializing a node. Initializing a node means that given a particular data and a particular pointer, you want to actually set these two values. So let me switch to the IDE. I have PyCharm installed, okay? And I actually have the full definition of the node class here. What you actually need to add in the paper is only these first 4 lines that basically define a class node with the init method that actually is the constructor of the class, passing self, that is actually a reference to the actual object itself, and the 2 values, data and pointer. And then you actually set data and pointer to 2 fields, underscore data and underscore pointer, to make them private. Underscore is kind of the convention in Python to make them private. You could even use 2 underscores. I honestly prefer 1. Up to you. I think the code becomes quite verbose if you use 2 underscores, but it really depends by your preferences. And I actually added, because I want to actually show you this code in action. Unfortunately, if you do the paper, you don't have enough code in order to be able to run it, but I wanted to show you just for the purpose of the learning. So I also implemented set data, set pointer, get data, and get pointer, right? That you are going to use it later. You need to kind of assume that you have this implemented already, but you have not been asked to actually add it in the paper. Okay, so next, what's the next question? So you now need to do the linked list class. So the linked list class has an head pointer, a free list of pointer, a node array that contains up to 7 elements of type nodes. So a linked list basically can have from 0 to 7 nodes. The constructor of the linked list, then there's a method that is find insertion point that actually find the previous pointer and the next pointer of the location where we want to add. You have not been asked to write this function in the paper. Add to list that actually add an element into the list, and output list to console that actually print the list on the screen. So this is actually the representation of the list. So I recommend you to actually look into your course book to fully understand how linked list works. So the idea is that you have an array, right, of nodes, and each node contains the data and the pointer to the next element of the list. And you kind of have 2 lists in the same array. One list is actually the actual list, and one list is a list of free pointers. Okay, and basically, if you want to add a new element, you basically use the first element of the free list pointer, and you add it in the right location at the actual list, and then you actually change the free list pointer to contain all the remaining nodes. So you have this sort of implementation. We need to kind of get our head around this because you need to implement something now. So first of all, you need to explain the meaning of the term null pointer. Null pointer is basically a pointer that doesn't point to any address in memory, right? Usually a pointer points to an address in memory, but in this case, an index, so a pointer is actually an integer that points to a particular element inside the node array. It could be 0, 1, 2, 3, 4, 5, 6, or 7. So they are the only available pointers for the particular in this particular case. So basically what it is pointer that does not point to any address. So the address could be actually real address in memory, or could actually be an index, like in this case. What is an appropriate value that we can use? The classic value that could be used when you implement linked list using array is -1, because you know that -1 is never a valid index for an array. You need to also say why -1 is appropriate, because it is not a valid array index, right? We know that the only valid array index are 0, 1, 2, 3, 4, 5, 6, 7. So the next step is to write some code that constructs this list. Again, the initialization of the list. So let's get back to the editor, and I have the code here. This is actually the code that you should write in the paper or something like that. So what do we have? So basically, you need to set all the variables that you've been given in the paper. One of it is the head pointer. So let's go back to the paper. So the head pointer is this one. So it's a number that represents the location of the first node in the list. At the beginning, it's going to be -1 because the list is empty. Okay. So at the beginning is going to be like this. Kind of draw the diagram. So at the beginning is going to be something like, can I type that? Like this will be the head pointer pointing to 0. So that means empty, no empty. So it will be -1 basically. And this actually is the head pointer. So this is actually the initial state, and everything will be inside the free list pointer. And then the free list pointer is going to be 0 because It's like that. The first element is going to be the first element of the array is actually the first element of the free list, and every single element in the sequence will actually be in the list. So we need to initialize that. So the node array at the moment is empty. We add all the nodes inside the array. So we need to add n, so 8 nodes, because the array is from 0 to 7. This means there are 7 indexes. So it means there are 8 indexes, 0, 1, 2, 3, 4, 5, 6, 7. So that are actually 8 nodes. So we need to add 8 nodes. So we can do a 4 in range 8. So basically E will be from 0 to 7. And then we create the node, and we use empty string for data, and it's basically it basically means that there is no data in it, right? Could be other stuff, but the most valuable things to set is actually the empty string, so there's no information. And then you pass the pointer, that is will be I+1. So this one is the pointer of the next node in the list, remember. So each node contains the pointer to the next node. So for the node at the address I, the next pointer will be I+1. So at the beginning, the free list will be exactly the order in the array from 0 to 7. But as you add stuff and remove stuff, eventually it might not be exactly the order in the array. And then you need to add in the node array this node. For loop, basically you added 8 nodes in the list, but at the end of this loop, the last node will be set to I+1. There will be 8, so will be set to a wrong index that is outside the range of the array, so that's not valid. The last element of any list should be the null pointer that we decide to be -1. That means that we need to set the last element of the list, so the last node of the list, to point to null. That means we need to set the pointers to -1, and this is it. This is actually how to initialize the linked list. Then the next things you've been asked to is to actually how to create a linked list called contacts. That's quite easy. You can just do contacts, then you do equals, and you call linked list like that in Python, right? I've got some code later on that I can show you. Then we need to implement output list to console. Okay, so this is basically the code to print all the data inside the list to the console. And I've got it here. This is actually the code. So what do you need to do? Okay, you need to start from the head pointer. Okay, so basically you create a pointer that actually is the same as head pointer. If at the head pointer is actually -1, that means the list is empty, nothing happened, right? So otherwise, until the pointer is not null, so not -1, we want to actually print the data at that location. So self node array of pointer get data will get the data inside the node at the location pointer, and they will print that. And then what we do, we actually set pointer to the next to the next address. So to the next pointer will point to the next node. To do that, you actually get the current node, and you call get pointers. That will be actually the pointer of the next node. That might be empty, might be the null pointer or not. So basically, we actually iterate through the list until we reach the end of the list that will be pointed to be null. And that's actually the code that you can write in order to actually print the list to the console. The last exercise is quite complicated. It's actually the code to add the list, the string to the list. But you are actually being given the code quite straight in text. So it's not as hard as it could have been if they didn't provide you any kind of guidance in how to do this. So you need to make a copy of the value of the free list pointer. Then you need to store the data in the free pointed in a free node, adjust the free list of pointer. If the linked list is empty, basically, so The idea is this one. You take the first node of the free list of pointers, right? If the list at the moment is empty, it means that this node will be the new head. So make this node the first node, and then set the pointer to the null pointer. So this basically happen. So these bits here happen only when you add a node at the first time. Oops, I don't know what I wanted. Only when you actually add a node the first time, you get that. And when you do the else, if the the find insertion point method is called, we return two pointers: previous pointer and next pointer. These are basically the pointers that identify the location where you want to add the new node. If the previous pointer is null, it means that the insertion point is actually straight at the beginning of the list, because the node where you are, if the previous pointer is null, means that there is nothing before that node. So it means that the new node will be added exactly at the beginning of the list. Otherwise, the node will be actually added in between. So the new node will be the new node, the new node will be added between the previous and the next node, basically. So find the insertion point will give you the pointers to the two nodes that should be before and after the new one that you are going to add. So it's a bit hard to describe. But you kind of translate this in code relatively easily if paying attention that you kind of have this find insertion point function that is being described here. So we actually return the previous pointer or the next pointer. And you are not being asked to write this find insertion point function, but I actually added it here because I want to be able to run this code. So you don't need to understand that. So this is actually something I created just to be able to provide you some information. So what I actually do with this function is just to return assuming that you are going to always insert at the end of the list. So if you add an element, it will be always added at the end of the list. But you could do any logic that you want, but it's not being asked in the exam. What's been asked is to implement the add to list function. So let's have a look at this. This is actually what you have to add in the answer here in this answer here. So let's have a look. This is actually the translation in code of what has been said in English. Okay, first of all, the new node pointer will be set to the free list pointer. Then we set the data at this location. So because we are actually using the first node of the free list of pointers, so we actually set the data to that. And then we get the next pointer, so the location of the address of the second node of the free list. And then we set that to the free list pointer. So basically, we update the free list pointer to point to the second element, because we now used the first three elements. It's not going to be free anymore because we'll be added in the actual list. So now new node pointer is actually correct. Actually contains the new data that you want to add, but it's not yet been added in the list. So, and here are the two cases. The first case is if add pointer is equals -1, that means that the list is empty. We need to actually add it. We'll make that the new first node. So this means that the add pointer is going to be the new node pointer, because this will be added at the top of the list. And but the pointer of this new node, you could have done that, or you could have done. So see, you take the node at the location new node pointer and you set the pointer to -1, because we know that this new node pointer doesn't have any successor. Pointer was equals to -1, it means that the list was empty. There was no successor. Okay, so after these lines of code, the list will contain one element that is just the new node pointer. Okay, otherwise, okay, we don't really know. We need to call a function called find insertion point that will return the pointer to the previous node and the next pointer. So the idea is that if I can do a quick diagram here, you will have something like that. Let's say we have a few nodes here. You might have this one to be the previous, and let's say this to be the next, right? So this means that a new node is relatively difficult to do this with this editor, but let's try. So let's say this is the new node I want to add. New node. Okay. What I need to do actually is to update the list in a way that this one point to this, and this one point to this. Okay. I want to insert the new node in between the previous and the next pointer, and that's actually what we actually need to do here. So that's why we have find insertion point. Will give us these two information. But if previous pointer is -1, so let's say this one was -1, when this happens, in this case, if let's say previous pointer is -1, it means the next will be this, will be the first one. So it means that I'm gonna add this new node straight at the top of the list. So let's say the previous was empty. I just have to do that. So there are two cases: when you add the new node in the middle of the list, or if you add it at the beginning of the list, but when the list is not empty. So we already covered adding this at the beginning of the list, but when the list is empty. But we might also have to insert the new node at the beginning of the list, but the list is not empty. Right? So there are three cases. So if the previous pointer is -1, it means that the list that the new node need to be inserted at the top of the list as the first element. So we take the node at the new node, and we set this pointer to point to the head pointer, because we want to point to we are in this case, we want to point to the head pointer. So this is the head pointer, right? Head. So in these cases, we set the pointer of the new node to head. That's what we did here. And then we set the head pointer to this new pointer. So we need to move this one. This one will actually become the head, because this one is not anymore the head. This will be the head. All right. While in this case here, what we do is we set the new pointer to be next pointer, and we set the previous pointer, the pointer at the location of the previous pointer, to be new node pointer. It's basically we're doing these two arrows here, and then we don't need to touch the head, because we actually added a node in between the list. So head is not going to be changing. It's going to remain the same. So it's going to take a bit of time for you to actually digest this. I understand it's quite difficult. Again, I hope that I provided you the code that you actually can play with and familiarize with implementing linked list in Python. So the fun part is now that actually I can show you this working, and you can actually debug the code on your own if you want to learn a bit more about how this works and to actually run this step by step. So what I actually do is I create a linked list, and I add Andrea to the list and add Tom to the list. And I might also add another element, like say I had Mark, for example. So when I run the first add to list, what happened, I'm going to execute these bits here. When I run the second one, I'm going to execute this one. And when I run the third one, I'm going to execute this one. Or might not be, because depends how you implement find insertion point. But yes, it will be. It will be, because the way I implemented find insertion point is always to return the last two elements. If you very quickly look at this, is that it's basically I iterate through the list, and then the previous pointer until I arrive at the end, and then basically pointer will actually be pointing to the last element, and previous pointer with the element before. So pointer will be always pointer will be always -1 at the end of this, and previous pointer will be always the last element of the list. So basically the way I do it is basically previous is going to be that, and next will be -1. So I always had the node at the end here. So that's basically what I did, what I implemented. But you can actually change my code in a way that might actually return something in the middle. You can customize that as you want. It was not part of the exam. But yes, in this case, the last addition should execute this code. So basically, you can test all of the code and step into it. And then I call output list to the console. They actually should print the names that you added on the screen. Let's try to run it. As you can see here, basically we get Andrea, Tom, and Mark printed. So it's actually working. It's pretty cool. And just to show you, you can actually put a breakpoint here, do debug, and then you can see that, you know, I'm trying to add Andrea, and I actually, the add pointer was -1, and then I'm going to set it, and I can actually iterate through this and see how the code works. Then I go into this. I see we always go in the last one. So feel free to take this code and play with it. I'm gonna push this into a repository, and the repository is actually here. It's github.com, Angela A, CIE-computer-science, and here you will find a folder with the for a particular paper. I haven't pushed that yet, but you will find this code here, and so you can actually play with it. Excellent. We actually finished the paper, I believe. Yeah, there's no other questions. So thank you very much for having the energy to arrive at the end of this, because it was quite a difficult paper. So there's a lot of digest, hash tables, and linked list, and I definitely recommend you to go and play with Python. Feel free to ask me questions on Slack or send me an email to angela.andrea.com if you need any question. And thank you very much.